Hello and welcome to this virtual session about OCP-Security common threats. My name is Igal Edry. I am the VP Products in Chameleon, an Israeli startup working in the hardware security space. Before Chameleon, I worked for Microsoft and I was the program manager for Azure Hardware Security. So I think I have a good perspective to share with you what it is that OCP-Security is working on and what threats are we trying to mitigate. Let's get started. So first of all, what are we going to try to achieve in this session? I'm going to try to walk you through the high-level specs taxonomy and terminology taxonomy of OCP security. This is the first session in the security track today, so I thought it's a good opportunity to use it to explain the big picture and not just focus on the threat model. Next, we will dive into the threat model. I'll keep it a high level. There is a spec that talks about the details, but in this session, I will try to basically summarize the key points and stay at the 10,000 kilometers view of the picture. Generally, we'll be looking at the threats we're trying to mitigate and which specs address those threats and have the necessary features to mitigate the relevant threats. And we will also talk about things that we left out of scope for V1 and why we did that. And I would say in advance that there are many cases where we can still improve and do a V2 with more tight security, but this is our V1, so we'll start with that. I'll also show you where you can help. There are several specs that can get some attention, so community help is always welcome. So first, let's talk about what specs actually exist. So I'll start with saying that if you go to the wiki page of the security workgroup, you'll see the full list of specs, and it's being updated as we decide on new specs, and there is a list there for the meeting schedule, etc. So if you want to track the work of this workgroup, bookmark this link. The first spec that I will basically talk about in this presentation is the common security threats, and you should think about it as the threat model for OCP security. It doesn't have any requirements by itself. It's basically a mapping between threats and the specs that actually address the threats by detailing the necessary requirements that need to be implemented. So real specs are the secure boot spec that talks obviously about how to do secure boot, attestation, secure update and recovery that talks about how to do firmware update and how to recover when firmware is corrupt. And there is a spec in progress for platform requirement that talks about what you need to do when you're designing a platform that needs to integrate OCP security into it, as well as security of the root of trust chip that we are speccing. Last but not least, there is a detailed document of best practices called Secure Firmware Development Best Practices, which was contributed to OCP by CSIS, a cloud provider, Cloud Security Industry Summit forum, which I'm also part of. And that complements the work that is being done by OCP Security, and we'll talk about that and when it's applicable and how to use it. So let's get started. I thought that before we dive into specific threats and mitigations, we need to get into some common taxonomy of understanding the system that we are trying to protect. So this slide is all about that. So there are some obvious terms here, like every platform has a CPU, probably has a BMC, has some memory. When we talk about platform, we think about the motherboard, basically. We also talk about devices or peripherals. So you should think of these as like any PCIe card or disk or stuff you have in the system. There is usually a flash firmware on the motherboard and maybe even more. that has the platform firmware, things like the BIOS, the ME, etc. And there is also a device flash, which is a flash on the peripheral itself that we will talk about. And next important terms to talk about are the root of trust. So we are talking about in the various specs and in the feature requirements and in threats, we're talking about a PA root of trust, the platform active root of trust, which is the root of trust on the main system. If you're familiar with the Cerberus, Titan, this is it, right? There is also a set of requirements around the root of trust on each peripheral. It can be a dedicated chip. It can be a set of requirements that you just implement. Here for generalization, I am treating those as if they are real components, real chips. But when you read the actual specs, you'll see that there is some flexibility of how exactly you implement that. But I thought that for simplicity here, we'll just assume it's another component. So PA-ROT and AC or active component ROT are two root of trust components that we'll talk about a lot. Next set of terms, we will talk about attestation. So in attestation, there is a tester device. So think of it as the peripheral that tries to prove to the platform or to the verifier that it's in a healthy state. So we'll talk about the tester, we'll talk about the verifier. Device attestation is basically the process of attesting a device by the platform. And there is also a thing that kind of very related is platform attestation. So how does the whole platform proves its state or its configuration or its security health to some management infrastructure that's external? We are not specing that. We'll talk about that in the out of scope section. So these are kind of the high level picture. And again, I want to emphasize that it doesn't mean that a system must be designed exactly as it's here. This diagram is a generalization on purpose, simplified on purpose, just to allow us to visualize the threats and where each spec is applicable. There is some flexibility in the actual specs. So let's dive into the actual threats and mitigations. I want to say one more thing. The deck is structured a bit differently from the spec, and that's on purpose. The spec has a very detailed list of threats and mitigations and which feature is applicable where. And here I try to bucketize it in a way that would be easier to explain and visualize. So don't expect this session to cover the entire list of all threats and all mitigations. It tries to take a few examples, the main ones, and talk about them and visualize them so that you would exit this session with a good understanding of the big picture. And I highly encourage you to then go and read the actual spec and the actual text there, and they obviously also provide comments on anything that you feel you can contribute to. So let's get started. First set of threats are basically around firmware integrity, or in another word, how do you know that you're executing the properly signed authorized firmware and not some rootkit? The threats could be like execution of unauthorized firmware. So someone actually tried to plant malicious firmware and you don't want that to execute. It could be attacks that involve rollbacks. So someone trying to attack your system by causing it to execute properly signed authorized firmware that has known security defects and then using those defects to penetrate the system. And third, it could be just like signing keys for firmware get compromised, and as a result, someone tries to sign something malicious and replace the firmware using the fact they have those keys, right? So the way we address those threats is by basically two specs. The secure boot spec talks about what integrity checks need to be done during boot. It talks about rollback prevention, how to prevent someone from installing firmware on a system that is of an older version than the baseline that you have set. And obviously it has support for key revocation for the case of compromised keys. So you can basically, once you handle those features, you basically have these features, you get a higher confidence in the integrity of the software of the firmware being booted. The second aspect of this is the secure update. There is a mechanism in the specs for establishing ownership over the firmware, which is, you can think of it as who are the authorized signers. Let's say I am Chameleon and I want my systems to only run Chameleon signed software. I can set ownership of the system and say it's owned by Chameleon. This is my public key. And from there on, the system will only accept Chameleon signed firmware. That's kind of the concept here. So integrity checks are not just done during boot, but they are done during updates, and firmware that is not properly signed cannot be flashed into the system. I would say that secure update spec is still under some work, but you should keep an eye on it, track it, and hopefully we'll get it released as soon as possible. Everything here that we've talked about in compromised flash of the platform is also applicable to devices or peripherals. So like your PCIe card or your HBA should follow the exact same practices, and the exact same features of secure boot and secure update should be implemented there. And this is how you also get integrity of the firmware on the device. Last but not least, you can have all of the integrity you want, but if the code has security bugs, exploitable security bugs, then the attack vector would be not by replacing your firmware, but just by using the firmware bugs in order to penetrate the system. So this goes to software bugs, firmware bugs, hardware bugs, and even things like just unsecure development environments. So malicious actors can plant backdoors in your code and manipulate the firmware during supply chain attacks and stuff like that. That's exactly where the document I talked about before, the secure firmware development best practices, comes in. It came as a contribution from the CSIS supply chain workgroup, which I'm working in. And we've recently made it available to OCP, not just as a document, like a PDF document that you can find on the website, but actually as a Markdown version on the OCP GitHub repository. So you can use it, you can contribute to it when you see improvements that you think we should add, or you can fork it and use it for your own needs. Often you have some specialized requirements in your environment, so we encourage you to fork it and create a custom version of it to you. But if you follow all of these instructions, you will get a very good set of best practices to follow, and that's it. Moving forward, so how do you gain trust in a platform? How do you know that secure boot was done properly, that everything is configured correctly, and that the platform can be trusted and be secure? So let's talk about that aspect now. Let's say you have a system that was misconfigured. For example, someone tried to disable secure boot, or someone tried to change some security setting that they shouldn't. Let's say someone installed a firmware version that you didn't qualify, you don't want to authorize it. Or even at the worst case, someone has tried to connect a different server to your infrastructure that either has a lookalike ROT component or something or doesn't even have it, how do you detect it and disallow a system like that to operate? So the answer to that is in the attestation spec. The attestation spec details the concept of how to do peripheral attestation, how to know that all peripherals are properly configured, how to know the system is properly configured, obviously. It basically is based on the concept of taking measurements of firmware, of configuration data. And also it uses the fact that the PA ROT, or basically any ROT, has to have an unclonable identity per each device. And then you can use this identity to verify that you are booting systems that are really part of your inventory. So that's really where attestation spec comes along and the type of threats it mitigates. Just like we've talked about platform and then about devices, when we talk about peripherals, they need to attest to the platform. And there could be several threats here. There could be a device or peripheral that basically lies, tries to give some fake measurements. And there could be attacks that involve man in the middle, someone listening on the bus between the device and the platform and trying to launch a man in the middle attack on that attestation bus. The attestation spec addresses those by having, first of all, the cryptographic protocol for how to do attestation and how to be resilient to man-in-the-middle attacks. Elaine, I'm sure, will cover a lot of details about the attestation spec and how exactly it's being done in her session. And second, there is this concept of a reference manifest, meaning you can the PA ROT can know the identities of everything that needs to be in the system, like the identity of the platform, the identity of each peripheral, etc., and verify that this is indeed what's there, and prevent devices with unknown identity to even get connected. There is a corner case here that I thought would be worth mentioning, which is there are cases where you have devices that are indirectly connected to the platform. So the best example is like an SSD that sits behind an HBA that connects to the platform. We've had some discussions about the model of how to support that. There is one option, which is a hierarchical model where the system knows the full hierarchy. We actually opted to go for a flat model where the system just knows the identity of all of the devices. And that means that devices like, let's say, an HBA card need to act as bridges and basically pass attestation data from indirect devices like the SSD all the way to the ROT. But again, it's basically all the same thing. When the platform boots, it needs to perform attestation to verify its configuration and the configuration and firmware versions of all of the peripherals connected to it, and basically admit them in if they are acceptable and block them if they are not. So that's what attestation does. It's really the way to get trust in your platform and the whole system. Let's talk about the ROT itself and how do we ensure that it is secure and that you can actually trust it. What makes the ROT trustworthy? Two types of attacks that or threats that we're worried about. One is like some malicious and usually very sophisticated attacker can try to tamper with the ROT chip itself. It can try to replace it with a fake lookalike, or it can try to physically extract secrets from it, etc. All of these will be addressed in the spec for the platform requirements, which basically give guidance to system designers, platform designers, how to design the platform the right way to accommodate for having an ROT on it, and also for whoever will manufacture ROT component chips, what is the kind of tamper resistance that they need to implement. Um, this is another spec that is currently work in progress, and I'm sure that we as a group would welcome contributions there. The second types of attacks is goes back to the how do you actually trust the ROT itself. Let's assume it was fully implemented, all the features are there, but still, if the ROT itself is compromised because, let's say, it has bugs, then it can't protect the whole system. This is again where the secure development best practices document that I spoke about before is relevant, the CSIS doc. We expect anyone who is implementing the ROT to follow those practices, and once we start implementing an open source version of the ROT, I'm sure we'll do the same. Obviously, any software will have bugs. You have to accept that. And therefore, there is obviously support for updating the ROT itself with new firmware whenever we discover future bugs in implementations. So this is addressed this way. Let's talk about the areas we didn't dive into too deeply, or made assumptions, or decided to put things out of scopes. So I'll start with the explicit assumptions. These are things that we are basically expecting to be there. We're not specing how to do them, but we're making assumptions that they will be implemented. So threat number one, which people love to talk about, is what do you do if someone comes and does some physical tampering to the platform? I mean, with a soldering iron, right? Let's assume they come in and they solder some new component onto the motherboard that sits on some bus and transmit the data outside wirelessly, things like that. The model in OCP-Security assumes some level of physical security, like is practiced in cloud data centers. So this kind of attacks could be also mitigated by supply chain controls and stuff like that. We didn't get into the details of what are the right practices, how to do that. We're basically just assuming there is some level of physical security that is in place that prevents something at this level from happening. So it's an explicit assumption. The second explicit assumption we're making is within the supply chain and the process of manufacturing a system, there is a critical moment of provisioning the ROT, where if you provision the ROT maliciously, you basically own the system because you can provision yourself to be the owner or stuff like that. We are assuming provisioning has to be done in a secure facility. We didn't go into details of what exactly it means to be a secure facility, but it should be a place where you really trust the environment, that you know that if that thing gets compromised, you may get a compromised ROT. So explicit assumption number two is around secure facility for provisioning of the ROT. The other thing we didn't touch is how to do platform attestation. We're basically deferring or referring to TCG. There is today TPM in most systems. You collect measurements for the platform. You can attest the whole platform using the TPM measurements. We didn't get into that aspect. So attestation for us is mostly around what's happening between the PIROT and the peripheral, not about what happens between the platform and some external systems. Let's move to out-of-scope things. So first of all, we don't deal with stuff like leaking secrets of the disk of a protected system. Okay, this is out of scope for the OCP-Security spec. If you decommission a system and it has secrets on the disks, you should still erase the disk. You should still erase any data that may be left on it. We are not dealing with that with the OCP-Security workgroup as of now, as of V1. The second one that I wanted to call out is we don't deal with vulnerabilities other than with the best practices that document that we've published, which is focused on firmware but can be applicable everywhere. So if you still have runtime vulnerabilities, that allows some malicious actor to take control over your platform by injecting code into the system in runtime or using functional bugs to make your system do malicious things. That's out of scope for OCP security. It should be just like clear that this is not what the intent of the specs is about. It's really about firmware integrity and about attestation or gaining trust in the system at the initial boot time. But once it starts running, that's out of scope for the current set of specs for OCP security. Okay, so hopefully this gave you the big picture, and you now better understand what we are trying to achieve here. Here is what I wanted to do next. First of all, if you have the cycles and the knowledge, please read the full specs and give us your comments. We are still working on the specs. Some of them are closer to being done and some of them are still work in progress. So feedback is welcome and help is welcome. You are most welcome to join the OCP Security Workgroup. We meet every Tuesday, 8:30 a.m. PST. Just call in and start contributing. You are more than welcome to say you have cycles and want to contribute to the specs, so just come in and help us. And there are many specs we decided not to invest in now due to capacity. I'm sure we can do more, so help is appreciated. And last but not least, again, if you're a firmware developer, everything we're doing here in the OCP security around integrity is not as effective as it could be if the firmware is of bad quality and have security bugs. So please follow the best practices, take a look at the doc. It's a really detailed doc with a lot of good tips and practices to follow. Those practices are coming not from an idealistic view, but they're actually, every tip there comes from something that the cloud providers involved in CSIS have seen happen in the world. I've seen people doing wrong. So follow those best practices and we can raise the quality of firmware in general across the board. There is always more information on our wiki, so bookmark that. And with that, I will thank you and open for questions. Thank you very much.